Hello, in this session, I will talk about the Taylor polynomials. We did cover the Taylor and Maclaurin series, and that's the formulas that we learned, that we actually developed these formulas. And all of them are the Maclaurin series, but Maclaurin series is the special case of a Taylor because it's centered at 0. Based on the formulas, we may notice no quantity is subtracted from x. Yeah, that means 0. 0 is the center. Yeah, just to clarify it. And the first one we did, yes, we remember it's the based on the geometric property that we didn't really use the Taylor formula. And also the last two, the arctangent and natural log of 1 plus x. Since the derivatives, integrals can help with this, we manipulate the first formula. But to get the Taylor series expansion for e to the x, sine of x and cosine of x, we did use the Taylor's formula. And we remember the Taylor's formula is the coefficient c sub n is defined as an nth derivative at the center over n factorial. That means that's the Taylor's formula. Okay, but now what we will do, instead of taking the entire series, that's how we talk in the previous lesson, we will actually try to approximate a function by just a finite number of terms. We will take a partial sum, but the partial sum in the power series, in the Taylor series, is called Taylor polynomial. Like for instance, if I will stop here at the x cube, we will say that this is the approximation of the function e to the x by the third degree polynomial. If we would like to have better, more accurate approximation, we can keep going. We can expand to the higher level of the polynomial, x to the power of 4, 5, 6, or whatever is desired. For instance, sine of x, I can approximate by maybe the 7th degree polynomial. I will stop here. Cosine of x, I can approximate maybe by the 6th degree polynomial. Then I will stop here. Yeah? Okay, that's the idea. And we did learn the idea of the approximation, yes, in the previous sections also. The linearization, for instance, this was the first degree because it's just the line, the first degree polynomial. That's the formula, yes? And function can be approximated by this linearization. Of course, near to point A, because when we will go away from point A, function and the curve, they go actually a little bit like in different direction. But at the point A, function and the linearization has the same value at A and the same derivative at A. And that's the point. And let's actually look at this really quickly. That's the linearization. We also learn, I can maybe have here the quadratic. That means this is the linearization, okay? But we also learn a little bit more accurate, and I mean higher degree, the quadratic approximation, if we remember this. Yeah, I think you do. That means the quadratic approximation was defined as a f of a plus f prime at a x minus a, just the linearization. And then we were adding additional term with the quadratic. 1/2 second derivative at a and x minus a squared. That means that was the quadratic approximation. Parabola maybe will fit a little bit better and approximate the value a little bit more accurate near A. And of course, in general, when we look at this, when we have function and its power series representation, Taylor series representation, this is the formula, nth derivative at A over n factorial, and then x minus a to the power of n. And let's expand this. If n is 0, this is f of a. If n is 1, it's the first derivative at a over 1 factorial, x minus a to the power of 1. If n is 2, it will be second derivative at a, 2 factorial, x minus a squared, and I can maybe list one more, third derivative at a, 3 factorial, x minus a cube, and so on. That's when we may notice that this is the linearization is just the first two terms. It's actually the Taylor polynomial degree 1. Quadratic approximation is the Taylor polynomial degree 2. And we can now, we cannot really, I mean, we don't have to limit ourselves to the quadratic. If we need more and more accuracy, we can keep going with this degree. That means this is the idea for today, to approximate a function near a certain point, near the center, by the Taylor's polynomial. Yeah? The choice of the degree is yours. Okay, and now I have just this, yeah. I think, yes, I think I said the first order, the linear approximation. We can use this as approximation because value of a and value of the function is the same, value of the derivative and value of the derivative of the function and the line is the same. And we can see here the same, that's the line, which line can deviate faster from the f of x as we go away from a, we can see. But for instance, the quadratic, which one? This one is the quadratic, yeah, will stay a little bit closer. And even if we will have the third degree, fourth degree, we will approximate, we will fit the line even better. Okay, and now let's look at these formulas one more time. Taylor series, we know this. If it's centered at 0 is Maclaurin. And now if we will take partial sum, we can see we don't have this dots, we're not going, we will stop at n. We will call that this is the nth degree Taylor polynomial. And we may approximate a function by the Taylor polynomial, but actually with any convergent series, f of x is the limit of the sequence of the partial sums, of course. Okay, and just to clarify, we remember Taylor series can be splitted for the Taylor polynomial plus the remainder. And now let's see, that's what, yes, we just said. In general, f of x is the sum of its Taylor series, because then n goes to infinity, that means it's a series. And we will say that Taylor's polynomial, it's theoretically an entire function f of x minus the remainder. It's because this is just the polynomial. We can see that's this. And yeah, I hope we okay with this one, because how can I maybe illustrate this? If this is the entire function f of x, we're doing the approximation by the Taylor polynomials. That's when we still have this error, which we will call the remainder. Okay, that means f of x minus that remainder, it will give us polynomial, Taylor's polynomial. And now let's look at this limit. This is theoretically constant with respect to this limit. That's the limit of the constant is constant. This will stay. And we also remember this has to go to 0 in order for the Taylor series to represent the function. That means this goes to 0, and yes, f of x equals to f of x. Correct? Just to be mathematically correct. Okay, and then the theorem, of course, if this remainder goes to 0, f is equal to the sum of its Taylor series on the interval of convergence, of course. Okay, and we remember a lot of this information from the Taylor series session video. This is 0, and it's not, if this, I mean, the limit is 0, it's not, this limit is not really easy to be proved, but whatever example we have in this class, yes, the limit of the remainder is 0. Okay, it's been one more time before we start attacking some questions. Taylor polynomial, the nth degree polynomial, we can see that's the formula, we know the formula. I is changing from 0 to n. If it's 0, it's just f of a, because fi 0 means a function. And then first, second degree polynomial, and the nth degree, x to the power of n. That's when we have to stop. Yeah? And then we will say 0 degree, the first degree. That means please note first degree, second degree, we will stop at squared, third degree, we will stop at cube. And yes, and we can keep, of course, keep working, but this will be the Taylor's polynomial. One more thing, because we can say nth degree Taylor polynomial is like partial sum, because we're taking just partial terms. But that number 1, 2, 3, that index doesn't correspond to the number of terms, because we may notice t sub 1 of x is the first degree Taylor's polynomial, and we do have actually two terms. We have the first one and the second one. That means not always, actually, usually number of terms, like for instance, this one is 1, 2, 3, 4 terms, but the degree is third. Whatever is the highest degree of the variable, that's the nth degree, that index will correspond. Okay, we know everything, let's start. Let's just list Taylor's polynomial, 0 degree, first degree, second degree, third degree of the function e to the x centered at 0. That's what we can do. You can definitely notice that this is the Maclaurin. This is one of the known, because we did derive. Okay, you probably notice I am first of all, I am rewriting the series, because it's infinity, x to the power of n over n factorial. Right? You know that formula? Yes, okay, excellent. And now we can expand. If n is 0, x to the power of 0 over 0 is 1, and then plus x to the power of 1 over 1 factorial, x to the power of 2 over 2 factorial, x to the power of 3 over 3 factorial, x to the power of 4 over 4 factorial, and so on. That's the infinite series. Now, if we would like to list 0 degree polynomial, it will be just a constant. The first degree Taylor polynomial, it will be constant up to the x. X to the power of 1 over 1 factorial is just x. Okay, second degree, we will list 1, we will list x, and 2 factorial is 2, 1/2 x squared. Beautiful, and one more, third degree polynomial will be 1 plus x plus 1/2 x squared, and I need x cubed. 3 factorial is 6, 1/6 x cubed. Okay, and now I have the graphs. Let's see how nice they fit. The pink curve is e to the x. This line is linearization, which is just 1 plus x, first degree Taylor polynomial. Second degree is that yellow parabola. Even better fit. Even if we're going away from 0, it's a better approximation. And t sub 3, the blue line, is the third degree approximation, fits even better. If we will increase the degree, we will fit the pink line more accurately. Okay? And now we can approximate, right? Okay, I think this is the solution. And one more time, some values. Okay. Okay, now another one, exercise number 2. Find the Taylor polynomial degree 5 for the function sine of x centered at 0, and now use the answer from A to approximate sine of 0.3. And because we know, for instance, that's the main reason. One of the main reasons. We can get values of the function sine of x for certain values, for instance, from the unit circle, sine of pi over 3, sine of pi over 4, sine of pi over 6. Everybody knows these values, right? Sine of 0, of course. But for 0.3 or for most of the values, it's not easy to approximate. That's why we will need the polynomial. And again, sine at 0. This is the known formula, Maclaurin. We did the full job on this. We did the full, like we derived the Taylor-Maclaurin series. Yeah, that means I'm just using my memory. Okay, -1 to the n, x to the power of 2n plus 1 over 2n plus 1 factorial. Yeah? Do you remember this? Yes, you do. Okay, that means the first term is positive x, yeah, if n is 0. And then negative x cubed over 3 factorial, positive x to the power of 5 over 5 factorial, x to the power of 7 over 7 factorial, and so on. That's the infinite series. But now we just have to list the fifth degree. That means I will copy the first degree. I will copy 3 factorial is 6, x cubed, and 5. 1 over 20x to the power of 5, fifth degree polynomial. If we will be asked to find the fourth degree, we will actually stop at 3. Because x to the power of 4, yes, x to the power of 4, yes, it's not there. That means it's 0 times x to the power of 4. Yeah, we will stop actually at 3. Okay, that means this is the polynomial, and now what we can do, we can approximate. We can say function sine of x can be approximated by the fifth degree polynomial. Could be approximated by higher degree, but we will just here do the fifth degree. 0.03, and we just have to substitute. And we will have 0.3 minus 1/6 of 0.3 cube plus 1/20, 0.3 to the power of 5. And we can see basic arithmetic. We still, of course, I still use the calculator, but we can see I at least have something. Because if we will have just this sine of 0.3, how we can approximate, how we can like, yes, what we can do. We can, of course, use a calculator and get the value, but that's not the point. Even the calculator or even some coding, programming will need a little bit more complex calculations. This one, just cube, we can even do without the calculator. Yeah, it will take a little bit of time, but the answer is, I think I have 0.2955 2925. Wow, that's the answer. Okay, I don't have the actual value, but let's look at the graph, and probably it's really, yes, really close, because the fifth degree will fit the sine of x quite well. Okay, let's see. That means this is, okay, that's the approximation, and that's the graphs. That means, let's see, even the linearization, even the first degree Taylor polynomial fit the pink curve. We don't even see the pink curve beautifully. Yes, that means this one. And well, the fifth one, the blue one, that means 0.03. It will approximate really well. Yes, it will approximate really well. Even if we're going away, we can see up to that point, up to even here, up to we can get quite good approximation. Okay, we do have actually, we can measure the error in this approximation, even if it's teeny tiny, even if it's small. Okay, we do have like an error bound or Taylor's inequality theorem, but this will be in the next session. Okay, today let's focus only on Taylor's polynomials. Okay, that's we good with this. Another number 3. Find the Taylor polynomial degree 5 of the function natural log of x centered at 1. That means this one we don't know the formula. We will just do from the scratch. We know the formula for the Taylor's polynomial of Taylor's series. Actually, not infinity. Let's just put n. Actually, let's just put n equals to 5. Okay, I derivative at 1 over I factorial x minus I to the power of, x minus 1 to the power of I, x minus the center to the power of I. Okay, that means always the first one is the value of the function at the center. Then is value of the derivative over 1 factor, first derivative at the center, x minus 1. Value of the second derivative at 1, 2 factorial x minus 1 to the power of 2. Value of the third derivative at 1, 3 factorial x minus 1 cube. Value of the fourth derivative at 1, 4 factorial x minus 1 to the power of 4. And value of the fifth derivative at 1, 5 factorial x minus 1 to the power of 5. And again, whatever I did, I will recommend that you will do the same. Say aloud and list all of the terms. That this table will help us to organize all of the functions and derivatives, and then values, respectively values at 1. Okay, that means function is natural log of x. First derivative is 1 over x. Second derivative is negative 1 over x squared. Third derivative is positive 2 over x cubed. Fourth derivative is negative 6 over x to the power of 4. And then the fifth derivative is 24 divided by x to the power of 5. Okay, now values at 1. Natural log at 1 is basically 0. 1 over 1, 1, negative 1, positive 2, negative 6, positive 24. Let's take these values and substitute. That means natural log of x, or actually, I can say the fifth degree Taylor polynomial for this is, that's 0, that means I can put 0, and then minus 1, let me put 1, x minus 1, plus the second derivative is, no, the first derivative is plus 1. The second derivative is negative 1, but we have 2 factorial. Okay. The third derivative is positive 2, but positive 2 over 3 factorial, which is 6, is 1/3. Right? That's when I'm doing this calculation. 1/3 x minus 1 cube, and then minus 6 over 24, which is 1/4. Yes, because 24 is the 4 factorial. 1/4 x minus 1 to the power of 4, and then 24 over 120 is 1/5. We can actually see nice pattern. 1/5 x minus 1 to the power of 5. That means this is the fifth degree Taylor polynomial for the function natural log of x. And also, instead of natural log of x, we may take some polynomial centered at 1, centered at 1. Okay, we did it. That's the solution. And exercise number 4, you can try to do exactly the same like I did exercise number 3, just different function. Exercise number 5, maybe we can do really quickly because cosine is our formula. Okay, that means this one, we don't have to do from the scratch. We can just say that cosine of x, Maclaurin. Let me put the series. That means starting from 0, ending with let's do the series form, starting from 0 and ending at infinity. Negative 1 to the n, x to the power of 2n, all over 2n factorial. Do we know that formula? Of course you do. Okay, that means when n is 0, this is 1, and then minus x to the power of 2 over 2 factorial, x to the power of 4 over 4 factorial, x to the power of, not 5, even numbers, 6 factorial, and so on. Okay, that means if we would like to have the 0 degree polynomial, I will just list one. The first degree let's say second degree, because we do not have the first. The first degree, I will still just list everything below x squared, which will be just 1. 1 minus 1/2 x squared. And the fourth degree, for instance, 1 minus 1/2 x squared plus 1/24x to the power of 4. And so on. That's a couple of Maclaurin polynomials, actually Taylor's polynomials at 0. Okay, and let's look at the graphs. We can see this is just the line. Even the line, even the constant fit at 0, fit the curve quite good. This is quadratic, this is the 4th degree, the 6th degree, 8th degree, 10th degree, and we can see how nicely the polynomial actually fit the cosine. Instead of taking cosine, we can take the polynomial. Such a good approximation. Okay, it's amazing, yes, how other functions can be represented by different functions, more simple. Okay, it's number 5. Number 6, maybe you can try, okay, because we have to do from the scratch because we don't know. Find all of what you have to do is the 4th degree Taylor polynomial. I can just list for you, and you can also say aloud, value of the function at pi/2, you can find, this is function, and then value of the first derivative at pi/2/1 factorial x over pi/2 to the power of 1, value of the second derivative at pi/2/2 factorial, x minus the center to the power of 2, value of the third derivative, 3 factorial, x minus pi/2 cube, and one more, value of the fourth derivative over 4 factorial, x minus pi/2 to the power of 4. Find all of these components, substitute, and pick the correct one. Yes, you can do it. And then you can also do number 7. Let's do number 8, okay? Write out the first 4 terms of the Maclaurin series for the function f of x if these informations are provided. Okay, that's we have the derivatives. I mean, I can say function f of x can be the first 4 terms. That's me. Let's see what this means. We need f of 0, okay, because this will be the Taylor. We don't know the degree, but let's see. F of 0 plus f prime at 0, 1 factorial x to the power of 1, f double prime at 0, second derivative, over 2 factorial x squared, 1, 2, 3, 1 more. Third derivative at 0, 3 factorial x cubed. Okay, that means the Taylor, it will be the 3rd degree because we will see. Okay, none of them are zeros. That's okay. Let me align everything nicely. Okay, f of 0 is 9 plus f prime at 0 is 4x. The second derivative, f double prime at 0 is 4. 4 over 2 is 2. And then the third the third derivative at 0 is 42. That means 42, let's maybe write here, divide by 6, it's 7, because 6 is 3 factorial. Okay, that means this is 7x, different color, no. 7x cubed, okay, that means that's and this one I can say 3rd degree Taylor polynomial for the function f of x. Nice, really nice. Okay, let's look at another one. I have 2 more, and then everything is yours. You can practice. This is also interesting. Suppose to the 5th degree Taylor polynomial is provided, centered at 4, we may notice, centered at 4 for the given function f of x. Now, we have to find out what is the first derivative of this function at 4, third derivative at 4, fourth derivative, and the 5th derivative. Okay, that's what we will do. we know the formulas. In general, the center is 4. Okay. In general, the 5th degree Taylor polynomial is, let's do it again. Value of the function at 4, value of the first derivative at 4, 1 factorial, x minus 4 to the power of 1. Second derivative at 4, 2 factorial, x minus 4 squared. Third derivative at 4, 3 factorial, x minus 4 cubed. Fourth derivative at 4, 4 factorial, x minus 4 to the power of 4, and one more. Fifth derivative at 4, 5 factorial, x minus 4 to the power of 5. Okay, so now let's take some colors. This is the value, yeah, they correspond. Let me nicely. F of 4, actually we are not asked to find f of 4, but f of 4 is 2. Now, this coefficient, yes, coefficient of x minus 4 is positive 3. That's, we can say f prime 4 over 1 factorial, which actually is 1, equals to 3. Then we can say the first derivative at 4, it is 3. Yes, just comparing the coefficient. Okay, now, x minus 4 squared, x minus 4 squared, the coefficient is 7, and the general coefficient is this. That means, let's say, the second derivative at 4 over 2 factorial equals to 7. Then, second derivative at 4, 2 times 7, 14. Beautiful. Maybe this. A cube. Yes, cube. That means this is coefficient is 5, and this is the general coefficient. The third degree, no. Yes, actually, the third derivative at 4 over 3 factorials equals to 5, because that was given. Then we can say the third derivative at 4 equals to 3 times factorial of 3 times 6, 30. Okay, and then let's do one more. I mean, we have 2, but let's see what color I can pick. Let's pick this one. Okay, fourth derivative, we can see we have nothing here. Then we will say that the fourth derivative, it's basically 0. Yes, it's 0. And then one more, let's do this one. The fifth derivative, this is the coefficient, x minus 4 to the power of 5, and this one is negative 1. That we can say the fifth derivative at 4 will be 5 factorial times negative 1. Negative 120. Okay? That's how we can compare the polynomial and the coefficient. We can really take the advantage of finding the derivatives. And the last question is this one. You can try the same thing. Let's try this one, okay? Because that's interesting. Find the 8th derivative at 0 for the function cosine of x to the power of 4. That means, first of all, please do not try to differentiate, like first derivative, second derivative, because it is lots of product rule we will end up with. We don't want this. Let's use the Taylor's polynomial. Or Taylor's series. Okay, cosine. Cosine of x, we know the formula. Yes, one more time today. Negative 1 to the n, x to the power of 2n, all over 2n factorial. When n is 0, we have 1, and then we have 2 negative, 2 factorial, positive, x to the power of 4, 4 factorial, x to the power of 6, 6 factorial, x to the power of 8, 8 factorial, and so on. Okay, now I will just substitute x to the power of 4 instead of x. It means the same thing. Negative 1 to the n, 2n factorial, and instead of x will be x to the power of 4, and since we have another exponent 2n, we will just multiply. Yes? 4 times 2 to the n, because when we have two exponents. Okay, it means now if n is, let's make the expanded form. If n is 0, this is 1. That's because if n is 1, this will be 2 factorial. Let me just do 2 factorial. And then n is 1. 2 times 1 is 2, times 4 is 8. Basically, we're multiplying by 4 each of these original powers. It looks like 4. Oh, I messed up this. Let's put 4. Okay, now that means 0, 1, 2. If n is 2, this is 4. 4 times 4 is basically 16. And then 0, 1, 2, 3. If n is 3, 2 times 3 is 6 factorial. 6 times 4 is 24. This is 16. Okay, and maybe one more. If n is 4, this will be 2 times 4 is 8. 8 times 4, it's 32. Okay, and now what we need a coefficient, because we need to find out what is the 8th derivative at 0. Yeah? That's, we remember, I will not copy everything. If x is taken to the power of 8, yes, the coefficient is negative over 2. I mean, I can maybe write this way, negative 1/2, because 2 factorial is 2. And this is the x to the power of 8. And then we also know that general coefficient, if x is taken to the power of 8, the Taylor's formula is the 8th derivative at 0 over 8 factorial. That means this negative 1/2 equals to this. That means let's write this one more time. 8, that means they equal to each other, because this will be the coefficient of x to the power of 8. 8th derivative at 0 over 8 factorial equals to negative 1/2. Then the final answer is the 8th derivative at 0. When we cross multiply, it will be 8 factorial over 2 negative. And we don't have to simplify because it's a big number. Yeah, if you think the 8th factorial is a big number, okay, that means it's negative 8 factorial over 2. That's how we use the Taylor's formula. Yeah. Okay, that means enjoy the Taylor's polynomial. Please practice all of them, even the questions that I skip. And the next, we will talk about the errors, the error bound. Okay, thank you.